Hello everyone, and welcome back to my SP2 channel. This is going to be about molecular effusion and diffusion, slightly different terms. We're going to go over the concept and then we're going to do a couple of practice together. Okay, so a couple of reminders. Number one, we talked about the most probable speed in one of our, previous videos. That is the speed that we expect to get for, the peak of the Maxwell-Boltzmann distribution, which is following this relationship, right? You take the square root of the 2r2 over the m to calculate the most probable speed. And you probably remember the R here is the gas constant. T is the temperature that must be always in Kelvin, and then the capital M is the molar mass. Now, this is telling us, like if you follow this equation, we can say that the higher the temperature is, the higher the most probable speed is. And that kind of makes sense because we have more kinetic energy. And the heavier the molecule is, the lower the the lower the most probable speed is going to be, right? Which is also makes sense. Now, the second term is effusion, which is the idea of the gas particles, the gas molecules that are trying to escape through a tiny hole and they are going into the vacuum without any collision with each other. So the chance of the escape depends on how fast the molecules are typically moving. Faster molecules are going to have, more frequently hitting the hole so they can escape faster. And then we have the diffusion, which is the spread of the molecules throughout the space or into another substance. Best example is when you use your perfume, right? The perfume molecules are going to spread out through the air in the room, and that's how you actually can smell it. Okay, so the law that is taking care of this kind of interaction, right, is known as Graham's law of effusion. Thomas Graham discovered the effusion rate depends on the molar mass. It actually goes by R1 over R2, which is taking the effusion rates of the two gases, 1 and 2. That is equal to the square root of M2 over M1, and these are the molar masses. So the idea here is the lighter the gas is, the faster it diffuses. You can also relate that to the molecular speed using this equation here. So the effusion rate is directly proportional to the square mean root speed, right? The URMS, as you remember. If you put them together, right, and do a little bit of rearrangement, that would give us the R1 over R2 that goes by the square root of the M2 over M1. Okay, so take a look at the examples. Here's the first one. That's what I have for helium, which is a really light gas. The molar mass is only like 4 grams per mole. And this gas is going to be effusing much faster than the oxygen gas, which is 32 grams per mole. So you actually can see that using the molar masses, right? So helium is only 4, oxygen gas is O2, so we have to go by like 32, right? That will be 32 divided by 4, which is the square root of 8. And that means helium escapes almost 3 times faster than the oxygen through the tiny hole, right, in our experimental setup. Okay. Now take a look at another example. You've got an unknown gas composed of homonuclear diatomic molecule. It fuses at the rate of 0.355 times the rate of the oxygen gas it fuses, and they have the same temperature. We'll try to figure out what is the molar mass of this gas so that we can determine that. We'll try to identify that. Okay, so if you follow the Graham's law, taking the ratio of the M2 over M1, right? In this case, the unknown is going to be the M1 and the M2 is going to be the oxygen gas. So we go by R of the unknown over the R of the oxygen, which is equal to 0.355. Then you plug them into your formula using your M of the oxygen gas, right, which is 32 grams per mole. And that would give us the 0.126, which is equal to 32 over the molar mass of your unknown, right? Okay. If you solve that for the unknown, it's going to give us 254 grams per mole. Now we have to identify this gas, right? Okay, so we know that it's homonuclear diatomic, so it has to be like X2. If you look at the X2, if you follow the X2, it goes by 254 divided by 2, right? That's how you can get the 127 grams per mole. And if you check that on your periodic table, it has to be iodine. So I2 was the gas, right? Excellent job, everybody. Thank you for watching this video. There are going to be a couple of more on this units. I'll see you then. Bye-bye.